afternoon. This is CIVE632, Computational Hydraulics and Hydrology, and today is Monday, November 15th, 2021. And the subject today is a continuation of the topic of numerical modeling. So I think I'm going to rehash a little bit for its importance as far as the work we have done. A couple minutes. Danny um, is a great contributor in our field. He was employed with the National Weather Service for more than 30 or 40 years. He unfortunately passed away in the year 2009. And Danny and I had kind of, should I call it corresponded? Meaning I would read his papers and learn, and he would read my papers and learn too. I mean, I say that with knowledge, of course. So we were kind of feeding back on each other. But the beginning of the, if you could call it the feedback, was this paper that he wrote in 1975. I read this paper. I realized that he had not completed the work, so I proceeded to go ahead and complete it. I thought I had a slightly better tool than he had, or similar tools actually. I actually had the non-dimensionality and so forth. But I'm not going to bore you to death with this paper. It's a very tough paper to read, and if you want to understand it, you gotta get paper and pencil. But let me just say that in the abstract, he's talking about numerical stability. He's talking about the von Neumann method. Um, he's talking about the thetas, the values of the thetas. I should mention to you as part of a history that one of the first concepts that I ever was faced in numerical analysis was in the year 1973 when I ran into or discovered the theta, the weighting factor. I was working with sand waves. That was my job at the time. Not water waves, but sand waves. But they're the same kind of. The equations are slightly different, but the methodologies are quite the same. And I learned that the theta had an influence on the results. And I was wondering why and how could I control the theta and determine the correct value? Because different thetas gave different answers. And theta is artificial. It's totally a total artificiality of the methodology. So eventually, of course, we found out everything that was found out, need to be found out, because we wrote that paper that we read last year, and we have another paper now that we're going to touch base today. But all that stuff is rooted on the work that Danny Fred did. So over here, I'm not going to go over this, but just so that you can see, he was talking about the implicit scheme over here, right? The implicit scheme, the derivatives, and so forth. Then he gets heavily into the algebra. Look at this. That is ridiculous. And I'm wondering if he ever made a mistake, I didn't follow through completely, then of course you're stuck. That's got to be, and I'm not sure, to be honest, at this point, whether he published this paper in a journal or something like that. He's plotting about, he's talking about the numerical damping and analytical damping, which is the R values of Lennard-Seed. Remember R1 and R2, which we're going to be talking about today extensively. But he called it C sub D for whatever reason. I don't know. I prefer the numbers R1 and R2. I believe those were the ones that Conch used, but they were originated by Lennard-Seed in 1965. And then finally, conclusions. He says numerical properties of implicit four-point difference schemes. That's exactly the same thing we did in 1978. Generalized expression was developed for the stability factor using the von Neumann technique, right? We know that. He talks about what is the stable range for the weighting factor. The truncation error, demonstrate this consistency of the scheme, etc., etc. Okay, so I'm not going to quiz you on this. This is kind of more of the same. Actually, this is the beginning of what we already did last week. But I thought for historical reasons that I should get into and show you the paper by Danny Fred. So this is the paper by Danny Fred. Now, the next paper is, this is kind of a rehash, right? I believe, if I recall correctly, is the green, is it showing green or not?
No, we just see you.
There's nothing shared.
Nothing shared. Okay, there's something in here that it is not quite correctly. How about now?
Yeah,
We see the green.
Okay, so the story of this paper is that we had worked on it since I came across the Kunch paper in 1977. And I realized that Kunch had some mistakes in there, as I mentioned many times. So I figured, let me redo the whole thing, and if there are any mistakes, I'll find them. And sure enough, I did. I found some mistakes in his expansion on the Taylor series and so forth. I don't blame him. You know, everybody can make mistakes. And so I found, I corrected it, and then I had a calculation on an algorithm and so forth. Then when Bhavya Bhupalapati came over to me when she was a student in the year 2015, I identified this project for her. I say, Bhavya, you take a look at this computation, you check it. First, I asked her if she was good in math. She said she was. I said, cool. I've had some very good math students, by the way, over the years. Thank God. So I said, I charged Bhavya with redoing the whole thing and putting it in a calculator, which is not easy, but it can be done, and then post it and write a paper on it. So this is the product of the research. And by the way, she got 3 credits for this. It's a non-thesis option that we have in the department. I think that has helped us, the program, very well. We used to have a thesis option, non-thesis option, which is strictly an exam. But the exam turned out to be just a rehash of things, and somehow we came up with the idea that we should do a mini thesis, and this is in fact a mini thesis. Okay, so let's review this, and I believe I already talked about this, but now with more knowledge of what we're talking about here today, I'm going to explicitly say a few things that I perhaps had not said before. A comprehensive review of the amplitude and phase portraits, right, at the Muskingum-Kunch. Expressions for the amplitude and phase convergence ratios R1 and R2, which we're going to emphasize that, are developed as a function of spatial resolution, L over dx. We reckon that L over dx is the fundamental value, or the fundamental parameter. L over dx needs to be high. 100, I feel comfortable with. 50, not so much. 10 is bad. If you have an L over dx of 10, it's not going to work for you. It's going to be inaccurate. It's going to be non-convergent and so forth. The Courant number is important because the Courant number is a rule. It's a law. Some schemes are unconditionally stable, like the Lee scheme. Some others, like the Shaki scheme or the Maka scheme, are stable only for Courant number greater than 1 or Courant number less than 1. So we need to keep track of the Courant number. As it turns out, in the case of the Muskingum-Kunch methodology, the Courant number equal to 1 or very close to 1, we'll see that, is the one that produces the best convergence. And when we have best convergence, we also have great independence, because convergence is basically, convergence is theory, and great independence is practice. And then the weighting factor. The weighting factor is related to the Cell-Reynolds number D, which we also use in the Muskingum-Kunch. It is concluded that the Muskingum-Kunch is a good representation of the physical prototype, provided the spatial resolution is sufficiently high. The Courant number is close to 1 in the weighting factor, and we'll see that the Courant number can be 0.9 and it looks good, or can be 0.1 or 0.2 and it also looks good. It cannot be 0.1. We already know that from our problem number 2, homework problem number 2. It could not either be 4 or 5 or 10. That's too high. We have not had any calculations of that, but definitely that deviates from the solution. The weighting factor is high enough, better if in the range 0.3 to 0.5. So we find that from this paper. We find from this paper that the weighting factor can't be just about anything. It's better that it be high, 0.3 to 0.5. Two online calculators of the convergence ratios, one theoretical based on dimensionless parameters and the other practical based on actual hydrologic variables, are developed and tested. We did this for the purpose of helping people when they're running this model. If they want to have like an EKG of what they're going to do, they could run on one of these calculators and figure out how convergent the models are supposed to be or are likely to be based on theory, based on the equations. Okay, so we have the introduction, and we already know that the Muskingum-Ganch method. Ganch elucidated the kinematic wave basis of the Muskingum-Ganch method. Correct. This revolutionary concept, that was revolutionary at the time, 1969, based on the matching of the physical diffusivity of Hayami, 1951, with the numerical diffusivity of Ganch, 1969, enables the Muskingum-Ganch to remain grid independent through a wide range of relevant parameters. Grid independence is the ultimate objective. Any model that is grid independent is a good model in numerical parlance. If it's not grid independent, it's not a good model. It's just a model, but not a good model. And we're looking for, obviously, for the better, the best model. It is worth noting that this fundamental property of the Muskingum-Ganch is not shared by other flood routing methods based on the kinematic wave. Certainly, the convex method of Marcus was not grid independent. And that's the reason that led the Soil Conservation Service at the time, now Natural Resources Conservation Service, to undertake the revision of the convex method. Actually, they junked it. They dumped it, and they put something else in there. Okay. Then we already talked about the convection equation, which is the same as the Muskingum. As you can see, we're talking about the same subjects here. Derivation of equations, we can go through this rather quickly. We already know these equations. We've repeated them 3 or 4 times. Basically, what we're doing in here, it bears repeating in here, is that we vary the x for the purpose of matching the diffusion of the grid chosen with that of the physical problem. That's exactly what we're doing. That's why we vary the x. If we don't vary the x, we wouldn't be varying the diffusion. So simplifying, in which the Courant number is defined as follows, we already know that. And we have the solution in exponential form, and we're going to rederive everything we did before, even though we are doing this for the second time, actually, for the second time. So replace the derivatives. I don't have to go through the math. It would be unnecessary. But it is highly detailed exponential mathematics, advanced mathematics. A lot of algebra in here. You know how algebra is. If you make one mistake, then you're done. I've given many examples of that. Of course, in this case, we do it 10 times. So there can be no mistakes after you do it 10 times carefully. Okay, so we got in here, look at these equations, they're crazy. Okay, trigonometric identity and Spiegel. We use a lot the famous Spiegel book. It's the Shams outline. Can you believe that? Shams outline. Everybody looked at Shams outline. Oh yeah, Shams outline. Everybody knows that. But it was very helpful. To me, it was very helpful. It got everything in there. All the tricks or the trigonometric or mathematical tricks are already spelled out in Spiegel, if you're careful enough to look where they are. So we look at this stuff in here, we operate, we consider the imaginary parts, we replace, etc., etc., and we finally get to the R1s and the R2s over here. You can imagine how tough this work is, plus the fact that you got to type it, and you got to type it correctly. We finally define the convergence ratios, R1 and R2, right here. And this is, like I said, a repetition of what we did in the convection equation. The difference is being that here we're presenting it in HTML and we are going to do the calculator. Amplitude and phase portraits. Now we plot the plotting of convergence ratios as a function of Courant number and spatial resolution leads to a set of amplitude and phase portraits. Now, Ponce did this, by the way, but he did it in a mistaken way. He wasn't using Courant number. He was using R, which is only part of the Courant number. At any rate, we felt that since we came after him, we did a better job. So we have these figures, okay, now we have, for x equals 0, we're going to vary x from 0 to 0.6, just to show how things work. For x equals 0, the Courant number, okay, now let me analyze in here for you the R1. The R1 is the amplitude portrait, we call it. So the amplitude, in other words, how the way the calculation is going to vary in the vertical direction. The amplitude portrait. For low resolution, we got 95%. Look at this. Red is low resolution. Black is the high resolution. For the high resolution of 100, we get 99.5, 99.9, very close. For 1. But if we have 4, then it detracts, right? Theoretically, it would be less in here. We could go less in here, but then we're going to find that other things are going to matter at that point, so we better not go that route. It is best, in my experience, to stick with Courant number close to 1, and that can be done in most cases, actually in all cases. The phase portrait, phase that depicts the horizontal movement of the wave, of the resolution, or rather the solution of the problem. The phase portraits, again, the reds are bad, the blacks on top are good, very close. And of course, we can go even to 200 and it will get better. Just don't overdo it. Don't go to 1,000. That would be too much. You already know why. That's going to be in the exam, by the way. Amplitude portrait for x equal 0.1. Same thing in here for 0.1. It gets a little better. We could compare these two side by side, but it does get a little better. I can't show you at this point. It does 0.1 is better than 0. Then the phase portrait, then the phase portrait for 0.2, and it's getting a little better more. So you can see that it's getting a little better. These are the same scale values. And look at this over here. You have this distance over here, and now compared to this distance over here, it's a little smaller, right? So it's getting a little better. 2.3, it's getting even better. Now the black curve is almost touching the 1, which is the correct value. It's correct for 1 now. Look at this. For 0.2, it is exactly correct for 1. You cannot see the difference between 0.99 and 1. Then the phase portrait gets even better. Now for x equal, that's for x equal 3. Now the phase portrait is even better. Look at that phase portrait. For high resolution is almost at 1. Actually, I wouldn't even say that it has already crossed, or it may be just at 1. For practical purposes, it's already at 1. Then for 0.4, it's perfect, right? For 0.4 is perfect, but the red's always bad. That's why I put it in red in there. And for 0.4, the phase portrait, interestingly, every one of these is crossing for the phase portrait at 1 for 0.4. And that's the reason why 0.4 works so well. Even if you miss it a little bit, even for the phase portrait, you'll still be at 1 for the rest of R2 equal 1. That's what we want, R2 equal 1. Physical celerity over, actually numerical celerity over phase celerity. Take that back. Physical celerity, no, numerical celerity over physical celerity. Then we get to 0.5, and at 0.5, all of them coalesce at 1. For the amplitude, but not for the phase. The phase, they cross at 1. That's why 1 becomes important here, because 1 is the better solution for this whole thing. You can still do it at 1.1 or 1.2 if you want to, but 1 is better. And we have run this problem many times. And between 0.7 and 1.5, it works fine. You can't really see the difference. We just state 1 because we feel that it is a good number, a good round number. But nothing would happen from a practical standpoint if you use the 1.2 or 1 point or 0.8. And then we further go from 0.5 to 0.6. Why do we want to do 0.6? I mean, we really shouldn't be going above 0.5 because we wanted to prove the fact that according to numerical theory, the problem starts to blow up after 0.5. It already blows up for the red. Can you see 0.5 with lower Current numbers? It would show instability. That's for the lower resolutions. For the red line, it would show instability for sure. Instability and non-convergence. Certainly you don't want this because the red's going up. So that means that it's not moving vertically, but it's moving horizontally, the way it should not move. It's giving you the wrong answer. By the time you're at 0.6, the R1 is going up. That means you're getting trash. You're starting to get instability. The resolution, the numerical solution is higher than the physical solution. And the red is bad. And the phase portrait, also bad. If you have a Current number high, God forbid, you look at this, it's coming up really, really bad. So as you can see, these are like EKGs of what's happening in the core of the computer, because we're getting the right numbers for the ratios between amplitude and phase, both physical and numerical. Okay, we conclude that the Muskingum-Ganch model is a good representation of the physical prototype, provided the spatial resolution is sufficiently high, the Current number is close to 1, the weighting factor is high enough in the range of 0 to 0.5. So we would say between 0.3 and 0.5. We recommend that. Although setting that up would be a little bit hard, but it can be done. So practical applications. In practical applications, the convergence depends on the values of C and the cell Reynolds number, which in turn depend on the hydraulics of the flow and the grid size. So we can calculate a set of amplitude and phase convergence ratios may be calculated. And we have all this algebra in here, which you already seen. And we can use the calculator online Muskingum-Ganch convergence ratios practical. So we have a practical calculation, not only just a theoretical. And for instance, we just have an example in here. Assume the following data set. Mean velocity 1.75 meters per second, mean flow depth 2.3 meters, mean channel slope 0.0013, channel rating exponent 1.6. So this is kind of like a rectangular channel, roughly. Flood wave time or rise 24 hours, reach length 4,800 meters, and time interval delta t 0.5. This problem is posed so that we can follow all the rules and get a nice answer, obviously. Application in numerical analysis, if you get the wrong input, you will get trash. You won't get anything. Application, so the input's got to be thoughtful, very important. Application of online Muskingum-Ganch leads to R1 is 0.99953 and R2 is 0.999915. Excellent. Success. I can't count so many nines out there because I set it up to work that way. Okay, the spatial resolution is 100, which is good. The Current number is 1.05, which is good. And the weighting factor is 0.385. We said that it was higher, it was better. So all these conditions are satisfied for this example, and we get extremely good example. There is no question in my mind that if we did this and tried its convergence, it would be almost perfect, as we have tried many times. Comprehensive review of the Muskingum-Ganch amplitude and phase portraits is accomplished. Expressions for the amplitude convergence ratio and phase convergence ratio are developed as a function of spatial resolution, which is important. Like I said, spatial resolution should be 50 to 100. Not less than 50, and certainly if you want, you can go to 200, but don't overdo it in the spatial resolution. Too much of a good thing could be counterproductive. The Current number, yes, we know more or less how that should be. It should be around 1. It could be 0.8, 0.7. It cannot be too low because it will blow up. And it can be too high because it will obliterate the result. It will not blow up, it will obliterate it. It will cut it out. And the weighting factor. Finally, we have a calculation. We have both the convergence theoretical, that means once and for all, and then the convergence practical for a specific data set for application. So with this, then, we finalize the Bhupalapati paper and with its calculator. And now we're going to be going into the next paper, which is, today's the 15th, right? The convergence. Okay, fine. So this paper has not been done in HTML already. So we're going to look at it in its original form, which I'm looking at right now. If we go back in history, what happened was this. At the time I was doing this, and when I went back to Colorado State in the year 1973, Professor Mahmoud, who was my professor at the time, I was working with him. I was assigned to him. Basically, Simons had a big program. He's got about 20 grad students, and he was the head of the building. He was the dean of engineering, associate dean of engineering. He obviously couldn't handle 20 students or something like that. So he had assistant professors out there that were helping the students. And I was lucky to have worked with Khalid Mahmoud, who was originally from Pakistan, and he had a project out there to measure the sand waves. Now, the sand waves are an interesting thing. These are not sand dunes, because the difference between a sand dune and a sand wave is in the scale. The sand dunes you can have on the surface of the bottom of the river. You have sand dunes, but these are sand bed, large waves, as opposed to like the same difference that you had when you had the kinematic wave versus the Lagrange waves. The difference is in scale. Likewise, in here we have a difference in scale. The sand bed waves are the large ones, the ones that were of concern of Professor Mahmoud at the time. He was Pakistani, originated in Pakistan, and he found a way of doing work in Pakistan, and he applied and got successfully a research program with the National Science Foundation to examine the propagation characteristics of these sand waves that had managed to be dropped or get into the link canals. The link canals of Pakistan are the ones that were built in the, I would say, in the, when would it have been? In the 60s and 70s. There were 12 link canals. These are large canals. But one of them was, or two of them actually, were operated, out of the 12 canals. A few of them were operated in the wrong way. You never know. There's a flood. They don't open the waves, the gates properly. So there was a flood out there, and the flood carried a whole lot of sand, and that sand dropped into the channel, right? It was an event. So then the question at that point was, how long is it going to take for that sand wave, huge sand wave, to move downstream so they would clear out of the channel? These channels had about 40, 50 miles. And that was a very important question. I mean, it had not been really studied at that point. And that's why Professor Mahmoud got that contract. And I was lucky that I was there at the right place at the right time. And when I got in there in 1973, he had just gotten this job or this contract. And I was there, like I said, at the right place at the right time. And he offered me this job, and I took it. I took it because I wanted to do this kind of work. And I was also interested in the fact that it definitely included travel. And travel has been one of my things to do over the years, as you guys probably know. I ended up spending a couple of months, I think it was a couple, roughly, in Pakistan doing the field work to do the final thesis that we did with Mahmoud back 3 years later, 73 to 76. Okay, So, so our interest was the sand waves. Now, later on, after I had finalized my thesis, I got interested in the water waves because it was the same thing. It was just the kind of the same methodology. So basically, we got it through the back door. We got in through studying the sand waves, and then eventually we ended up in the water waves. And the water waves are more practical, are more popular, are more understood by a lot of people, right? For one person that does for one person that does bed transient routing, there's 100 that do flood routing. So it was only a matter of time before I got to flood routing because it was the methodology was the same. In other words, I was hired to do bed transport, implicit bed transient models by Mahmoud. And then 3 years later, I ended up becoming a very big researcher on floods because the, that was the thing to do to follow through. After I had gotten my PhD, I went into floods for a long time, as a matter of fact. I was actually outside of the control of Professor Mahmoud anymore. We had graduated, right? As a matter of fact, Mahmoud actually left. He went somewhere else at the time. So anyway, let's not get lost here on stories. But when we did the convergence of the water waves, then we proceeded to follow with the convergence of the bed transient models. In other words, of the sand waves, the convergence of the sand waves. So this paper is very similar to the previous paper. And the order was an interesting order. It was first the theoretical water waves, which led to the esker. I got that published, thank God. The second one, the theoretical bed waves. In the theoretical bed waves, for some reason, it uh, it uh, it did not get published. I must have not researched the subject completely. There were some people like Kennedy and others that have done papers. I thought I had covered it, but I didn't. So I got shot down on the theoretical paper of the transients. I wanted to do similar to the water waves for the sand waves, but I couldn't do it because I got shot down. So then the question came up to do the convergence papers for the water, and we did. We already read that. And then the question came up to do the convergence for the sand. But then the issue was I could not talk about the theoretical answers for the convergence of the sand bed models because I did not publish the physical, or rather the theoretical paper. So then I decided to include the paper that had been a little bit of the paper, not too much detail, of the paper that had been shot down and put it into this paper. So this paper really comprises both. In that sense, it's kind of a summary, and it may be hard to read, but so be it. So this is the same thing that we did for the S-curve. The only difference is that here we're going to be talking about different equations, the sediment equations, not the water equations. Methodology is the same. We use the von Neumann technique for the systematic analysis of stability and convergence. The method applied here to study the convergence properties of implicit numerical models of bed transient propagation. Conge and Pedro, Conge had written an interesting paper on this. This is how I learned how to do Conge. I came across Conge because Professor Mahmoud back in 1973 handed me this paper, and he says, this is a paper you got to read. Conge and Pedro. And then subsequently, we wrote a paper on it. Mahmoud and Ponce have developed numerical models of bed transient propagation. Analysis presented herein shows that it is possible to isolate the relevant friction and transport parameters, thus providing an increased understanding of the convergence properties of implicit bed transient models. Suffice it to say at this point that at that time, nobody, hardly anybody, I should say, had ever done numerical calculations with bed models, transient bed models. People have done a lot of flood routing, but not transient bed models. So we were among the first ones that were doing this. Subsequently, there was the HEC6 and all sorts of other stories that came about from the Corps of Engineers. But that's really a long, convoluted story, which I may touch upon later on, not right now. We have a job to do right now. We have the governing equations, the continuity equation of water, the sediment continuity. This is an infamous, why should I say infamous? This is a famous equation, actually. I apologize for that. It's a, it shows the change in bed load plus the change in time of the concentration plus the change in time of the bed going up or down. It turns out that the change in time of the concentration is an extremely difficult subject to handle it, so we dropped it. It's not perfect. So we basically said that if there's sand coming in into the reach, into the control volume, and it does not come out, it's because it dropped into the bed. And that's typically the way it happens, actually. When there's a gradation or degradation, that's the way it happens. So the second term is, if it's there, it is small and hard to determine. The equation of motion, the same equation of motion. So we got three equations in here. The equations of friction, bottom friction, our famous equation here that we always used. I started using this in my dissertation, by the way. And the story I think I may have told you is that I like Chesi, and I like dimensionless Chesi. But I realized at the time that Simons in his papers had used this. But I felt that it was better, or rather, he had used C, or better yet, C over square root of G, which is the square root of the reciprocal of this value. But I thought that was that intermediate. It was intermediate. So I decided to do this. I do not recall at the time that this was done. It's such a simple thing that anybody could have done it. But the fact of the matter is that we were among the first to do this. And I'm so sold on this equation that I actually put it in my book, risking a lot of things. I'm not going to get it there. But let's say that it is part of my book also. I shouldn't say risking. I actually solved completely the water surface profiles equation using this, none other than this formula, which those of you that took open channels with me will recognize. So that this is a good formula. It's a Chesi formula. That is why I am sold on Chesi rather than Manning, and you heard me talk about that already many times. Okay, so we got in here for steady form, likewise, etc., etc. So we're following here with the equations. Okay, see, we have to model the bed material here. We're talking about transport, sediment transport now. And of course, there's 50 formulas for bed material. One is more complex than the other. They're all fuzzy. They all give a cloud of answers. So I decided I wasn't going to do that. I took the Colby type relation of the form, this form in here, that the sediment transport per unit of width is an exponential form of the mean velocity, where K and M need to be determined. They are empirical. There are values that for this. Okay, so I took the shortcut in here. I wasn't going to get, my objective was modeling the sand waves, not doing sediment transport. Imagine that the object of sediment transport is very complex. And even Einstein, when he wrote his paper, his famous paper in the year 1950, he said he was going to stick himself or strictly do only steady flow. He wasn't going to do unsteady flow. Why? Because steady flow hadn't been done. How come he was going to go to unsteady flow, which is more complex? So the entire Einstein contribution of 1950, the famous Einstein contribution, is steady flow. Now, Colby was an interesting guy, and this is part of sedimentation, by the way. He pursued the Einstein method afterwards, of course, 1955, I believe. I have not actually gotten a detailed hold of his biodata, but Colby, I believe, was working with either GS or the Bureau of Reclamation. But he came up with modified Einstein in 1955, I believe. Colby felt that it was necessary to control and modify the Einstein, and so he came up with the modified Einstein method, which is, by the way, the method that is used in practice. We've actually developed a calculator for the modified Einstein, which has been interesting because it has been used all over the world, and people really don't have to go anymore into those awful Einstein charts in order to get the answers because I took the job of putting all the charts into a digital form. It took a whole summer back in the year 2008 when we'd spent the whole summer working on this project, which was a very worthwhile project. Simplified equations. We got the simplified equations in here, and I'm not going to bore you with the math. I mean, this is similar to what we did in the S-curve. If the S-curve was difficult, this one is, so be it, is the same. Linear stability analysis, same thing in here, the same equations, analytical solution. You can see these are equations that repeat themselves from what you have already seen, in which sigma is 2 pi over L times L sub O. L sub O is defined as d sub over S sub O. This is perhaps the most important concept in numerical analysis and hydraulics that I have contributed. I should claim that. I should have contributed. Lighthead and Whittam identified this value, but they said, well, you know, we got this value. It looks like it's important. But we actually applied it into the equations. How did we do that? Just trial and error. We were there, persisting. More perspiration than inspiration. We spent a lot of time trying to figure out which one of these values were going to be the one that was going to non-dimensionalize the equations. And we hit it right. The celerity, the delta. So finally, we get the celerity over here as a function of the Froude number and the delta. The delta is the attenuation, by the way. It's the log decrement. It's the same concept. So interestingly, now we have these curves of celerity and delta, which you will recognize that are quite different, similar, but the abscissa and ordinates are the same, but the curves are different. This is not an S-curve anymore, right? Remember the S-curve of the water? Now we got this curve that says the following, that for the very long waves means L great, meaning sigma short, the tendency for the celerity is to drive itself to zero, meaning it won't move. And that accords with reality. See, the reason why the wave is moved is because of the difference in momentum between the back and the front. The water is actually pushing the wave. The wave is interfering with the water flow. So therefore the water is pushing the wave. But if the wave is too large, then the water has really no momentum to push the wave. So therefore the celerity turns out to drive itself to zero. Okay? But if the wave is small, meaning L is small, therefore sigma hat is large, then it gets into a constant with the Froude number, which, by the way, this had been already demonstrated by previous researchers. As far as the attenuation, of course, people hadn't figured that out before because we had the tools to do it, this system of linear stability. We figured out that the attenuation was going to be very high when for the large waves and very low for the high waves. In other words, a high wave is going to have a tendency to persist. I'm sorry, a short wave, like a small sand ripple or dune, would have a tendency in between ripples and dunes. Ripple is a dune that is very, very small. Technically, ripples is not the same as dunes, but they kind of look the same. The only difference is they have a difference in scale. So in here, we're going to have movement. We're going to have, no, I'm sorry, attenuation is high for the small waves and not so high for the large waves. That means the large wave, we have a tendency to move downstream. So then we have the numerical solution. And like I said, this stuff gets really, really intricate. And all this stuff in here, and eventually we'll get to the convergence analysis, which is our 1 and our 2. And look at this. These charts are similar to the ones we have done before. And I'm just going to look at the success in here. I'm going to say that for the large waves, no, this is resolution. This is resolution. This is for the different sizes of waves. When it's very long waves, it's kind of misbehaved in here for the theta, but in here is very good, and in here is also very good. In other words, for the short waves, it kind of has a tendency to get better and better. Note that for theta 0.5, there's strict convergence, right? 1, 1, the number is 1. For 0.6 or 0.7, there's not, there's a certain amount of attenuation in there. It's kind of strong, okay? In the resolution for the different Courant numbers, this is for 40 actually. This is for 40. While these are 10, 100, and 400. Look at 400. 400 is perfect. 400 is perfect for just about any fruit. They all match, and it doesn't matter with the data. So these charts give us a good sense of what we should be doing. We should have a high resolution. We should have a theta 0.5 or 0.6 at the very least. We don't have to go above that because we're still good. Over here, we're still good. We definitely should not go below theta 0.5. I would say 0.55 would be appropriate, given the fact that we're not going to lose a lot if we use 0.55 for this kind of stuff. Okay, in the phase, this is the phase. In the phase, we have in here for pi over 40, this is the mid resolution, and we have pi over 10, coarse, middle, and very high resolution. Look at the high resolution for the phase, they almost look like they were gonna hit. They were gonna, if all of these coalesce to 1, then that's perfect. That's a perfect solution. Conclusion, the higher the resolution, the better the answer. The lower the resolution, pi over 10 will be very low, and then we got this stuff in here, which is a mess, right? We don't want that because we don't even know what the theta, the correct value of theta would be because they are crossing at odd values, not at 100, at 0.5, but rather higher values. So we want to stay away from that. So summary and conclusions. A comprehensive theoretical treatment of the convergence of the 4-point implicit numerical model of alluvial channel bed transient is presented. Convergence is tested by establishing the ratio of celerities and the ratio of attenuation factors. 2 physical and 3 numerical parameters. The equilibrium flow fruit number, and not a whole lot of sensitivity on that. The transient flow dimensionless wave number. The spatial resolution, very important. The Courant number, secondarily, but important too. And the weighting factor, which is all important, obviously. And these are Priceman schemes. So the weighting factor is important. And like we reiterate in this case, as well as with the water, the weighting factor of the Priceman scheme should be above 0.5, but preferably not greater than 0.6, between 0.5 and 0.55. Why should be that? The reason is because we would like to have it at 0.5, but unfortunately, at that point, the system is built in such a way that it has no way of attenuating any kind of noise. And I say any kind of noise with ignorance, because I don't really know what's going on in there. All I know is that the system has a tendency to become unstable in the long run if you run it with theta equal 0.5. So if you want to solve a problem or get yourself out of the problem, all that matters is that you'd use 0.55 on that order, 0.55. And then it was like an aspirin. It is an aspirin. I refer to it as an aspirin. It's a correction. It's not perfect, but it's good enough for practical purposes. So that is basically this paper on the convergence. As you can see, many of the things that we said for the convergence of the bed transient models are reiterating in more or less the same vein of what we did when we did the water models. Okay, so we're a little bit ahead, and what I'm going to do is I'm going to proceed because I do want to spend time on the applications. I'm going to extend myself on the applications. So I have about 20 minutes in here, 25 minutes actually, and I'm going to get started on the convergent explicit groundwater model. The convergent explicit groundwater model. This is a 2-dimensional model. The math is higher than the 1-dimensional model. Funny this, it may look, but it is. We developed this model with Cesar Erkan after I had read the O'Brien, Hyman, and Kaplan, because I already told you that when Cesar Erkan came to me in the year 2000, he said, we better do a model. We were doing the modeling, the climate. We were modeling the climate of the Ojos Negros Basin in Baja California, in Mexico. I had somehow managed to get a grant from an institution that funded projects along the border. It was along 100 miles or kilometers, I'm not sure. I think it was 100 miles. 100 miles north and south of the border. They were trying to help the border. Okay, the border region, they had money from government allocated by the US government. So they were giving out for many years, actually. I'm not sure if they're still in business or still instrumental in developing these grants. But at the time, they were small grants. They were, I think, typically $50,000 per year that they were giving out. So I applied and I got one. And my project was on the climatology of the Ojos Negros Basin, because I had visited the basin and I thought that we're going to discuss this later on in some detail in the environmental class. Climatology, I had visited out there and had received complaints that the weather was changing out there. People that have been there for many years decided the weather is changing. And it wasn't necessarily warming, it was not global warming, it's just that it was changing. So we focused on the climatology, but then eventually we got into the subject of interdiscipline. We decided that we started on the climatology, and we got to the hydrology, we got to the ecology, because it's all related. And that, of course, led me many years later to study the eco-hydroclimatology, which we have already read as part of our environmental hydrology class. As a matter of fact, I should confide to you that I'm actually working on a video of that paper. It's going to take me a month to do, but it will get done. A video on several videos, 4 videos on that paper. What is it called? The hydroclimatological research, the case for geomorphology. Because over the course of my career or my studies, starting with the work that I did on the Pantanal of Mato Grosso, I became convinced that it was geomorphology. That all the other sciences, related sciences, were kind of subservient, if I could express it that way, to geomorphology. The geomorphology ruled because gravity, closely tied to geomorphology, is gravity. And what can we do about gravity? Gravity is there. There's nothing we could do about it. So geomorphology was important, and I ended up writing that paper, now developing into a video of how geomorphology, the understanding of geomorphology, is important. And one of the things that I got from our study in 1995 of the Pantanal was that, of course, I was steeped in geomorphology and hydrology and geology too. By the way, I'm not a geologist, but I'm very confident with it. And so all I needed to do was learn ecology, and I did. I learned ecology. So I put those 4 things together. So in the year 1995, I was highly qualified to do our second Pantanal study. Yes, our second Pantanal study, the one that got published on my site. The first one I never published, and I actually have kind of lost track of that report, unfortunately. But the second one, we published that report. I lost my train of thought in there for a minute. Okay. Let me go back in here and say that we decided to do this model, and we used the model that is stated in O'Brien, Hyman, and Kaplan paper to solve the 2-dimensional elliptic diffusion equation. So I told Erkan in no uncertain terms, I said, we're going to do this. It takes a couple, 3 weeks, but we're going to have a lot of fun. And we're going to learn on top of it. So we did. We had a lot of fun, we learned, and we didn't have to buy a model. When you buy a model, I mean, you can get quick answers, but you never know. You never know, really. If you didn't develop a model, you technically never know, unless you have a lot of experience with it. Experience developed through years. And I'm saying about HEC1, I'm sorry, not HEC1, but HEC models and so on and so forth. Likewise with ModFlow. Many of you may have run ModFlow. ModFlow is a good model, but it's got a lot of quirks in there, and it would be hard to say that you got the right answer. There's a lot of things in two-dimensional modeling, particularly in groundwater, which we're going to deal today with, that cannot be answered, simply cannot be answered. We know for a fact that when you model, there's two things in there. There's the interior points, which everybody, you can choose the scheme and look at errors, convergence, stability, etc., and you can come up with an answer. But the model is not just the interior points, it is also the boundary conditions. And as far as the boundary conditions for a groundwater model, if in a channel model you have an upstream boundary and a downstream boundary, there's two, right? But in a groundwater model, you have a 10 by 10, so that's 100 by 100. We had 100 by 100. So we got 400 points that we got to define as far as boundary conditions. 400 points. How are you going to do that? Well, we do it because God is great. I mean, we try this and try that, and we have the theory behind us, but in order to do a satisfactory modeling of groundwater, you would have to spend a heck of a lot of money trying to figure out with precision the exact nature of the boundary conditions. And it's very hard to do. Certainly, we weren't going to do it in Mexico, in Baja California, because we just simply didn't have the data. But we did it anyway based on knowledge that we already had. You can run a model. Anybody can run a model. The question is whether you can run it accurately in the best way you can. So let's go back here with no further ado on what we did in here. This is going to take some time, and I believe we're not going to finish today, but I'll get started. I'll probably do half of it. It's very detailed, and it has a lot of information in there in the way of how to conceptualize and how to run a two-dimensional model. And we are going to get in there. My last class is on the two-dimensional water model. And this class is on the two-dimensional groundwater model. Okay. A stable and convergent numerical model is developed herein. Stability being a necessary condition for model operation, the emphasis is on convergence. We already discussed that. Significant feature of the model is its simplicity, which makes it attractive and useful for a wide variety of applications. In other words, if you had to redo MATFlow, it'll take you 3 years. If you had to redo what I have said in here, it'll take you a week or two, if you know what you're doing. It's just one equation and a bunch of boundary conditions kind of thrown in there. So anybody can do it. This is the poor man's, if I may say so, the poor person's, not to become single here, the poor person's groundwater model. Anybody could do it. Really, anybody could do what I'm going to present here today. Okay. A significant feature is its simplicity, which makes it attractive and useful for a wide variety of applications. It's an explicit formulation of the two-dimensional diffusion equation of flow in porous media for a homogeneous isotropic aquifer. What does that mean? Well, the aquifers are not homogeneous, and they're not isotropic. But we got to start somewhere, right? That's basically it. Homogeneous isotropic means that the two properties, which are the porosity and the storage and the transmissivity, basically, does not vary in any direction and so forth. It's constant. Sources, which is percolation from rainfall or irrigation, sources into the model, into groundwater, and sinks, pumping, are accounted for. So we can pump out anything, anywhere out of this model. That's exactly the way people would use it. They would say, let me pump in here 100 liters per second and see what happens to the groundwater. And by the way, we ran this model in the Ojos Negros Basin because we had some data, and we were able to get very reasonable answers. We found out that if we wanted to recover this, if we stopped the pumping altogether with aim to recover the basin, that it would take about 16 years for that to happen. in conjunction with what are the properties of the aquifer, of course. Boundary conditions are specified as head or flux, and permeable or impermeable. Head meaning the elevation, and flux is the discharge through a cross section, and permeable or impermeable. Are the issues permeable or impermeable? And that's something you have to locate in the field. And if you don't have a whole lot of data on the geology, well, you're stuck. You gotta make some assumptions. And we did some, by the way. Fortunately, I had Mr. Shetty, who had a lot of experience running mud flow. So I said, Shetty, this is kind of mud flow. It's another mud flow, somewhat differently. And so he did his own thing, and we calibrated, quote unquote, the model. Because the word is play around. We got to play around with the boundary conditions until we're satisfied that things are working reasonably. Specific model or specific focus of the model is the assessment of stability and convergence. There's another thing here. When you develop a model, you have to do two things. As we had said earlier or before in our previous papers, you got to do a theoretical test to see the accuracy or the convergence of the model under highly specialized conditions, initial and boundary conditions. In other words, the model has to work in the laboratory before it actually is used in the field. That kind of reiterative or redundant. Let me repeat it. The model has to work in the laboratory before it's used in the field. If you don't test it in the laboratory, then don't go to the field and claim that it was working fine. If the model works fine in the laboratory, it may or may not work in the field. But if we don't know, then it's not good. And we know that we can come up with any scheme, and we always have to test it, test the stability, convergence, and so forth. Fortunately, now we have the von Neumann approach, which is very popular, and anybody could use it, as we have studied here, to analyze stability and convergence. Okay, we show in here that this model must satisfy a convergence criterion if accuracy is to be maintained. The satisfaction of both stability and convergence requires that the cell Reynolds number D be equal to 1. Now, you remember that in the previous class, I said that the diffusion parameter did not have a proper name. Remember I said that? And I actually complained. But then later we said, oh, to heck with it. We're going to give it a proper name. We're going to call it cell Reynolds number. Why? Because we're going to call it cell Reynolds number because it doesn't have a proper name in the literature. I had Shetty and Erkan that worked with me 20 years ago actively looking. Let's realize though that at the time Google was not very well established. But still, we were looking actively everywhere, in the literature, in the library. We would go to the library, check out. I said, I want the proper name of that value. And both Shetty and Erkan came to me saying, Professor Ponce, we can't find it. We never heard of it. It doesn't exist. Now here we gave it a proper name. We call it the cell Reynolds number. That is just a ratio of diffusivities. Diffusivities, physical diffusivity to numerical diffusivity. After more than 20 years of implicit model development, namely mud flow, the choice of an explicit model at this juncture requires explanation. It is well known that implicit models are unconditionally stable. Sure, yeah, right. I mean, we can even get an explicit model, which is unconditionally stable. That's the Lee model. So the myth of only the implicit models are unconditionally stable has been demonstrated. Okay? Stability or unconditional stability, or I guess you can say stability or instability, depends on the scheme and the way it's set up and the boundary conditions, etc. It has nothing to do with implicit or explicit. Okay, now, lesser known is the fact that implicit models are subject to a convergence criterion, which effectively places an upper limit on the time step. In other words, people argue, they say, with a stability number, let's call it Courant, cell Reynolds number, because this is not hyperbolic, it's parabolic. So this is the cell Reynolds number. With a cell Reynolds number less than 1, it's going to be unstable, but if you increase it If you use the implicit model, which is stable, then it doesn't matter. The Courant number doesn't matter. But the point that we're making it here is very crucial, that you have to use it with a low Courant number, because if you use 4, it won't work. It will be stable, but will be non-convergent, and we know that. Examples of lack of convergence in surface water and sediment transport have been documented elsewhere. Okay, so the model formulation. The three-dimensional diffusion equation for flow through porous media is written in my book. It's from Rushton and Redshaw. Kresick. So you can see dx, dy, dz plus w. W is the volumetric flux per unit volume, representing sources or sinks. In other words, rain or pumping. That's W. And S sub S is the specific storage of the porous material. That's the time factor, as opposed to the X factor. As you can see, this is a diffusion equation in 3 dimensions. It is parabolic. It's a diffusion equation. Similar to if we drop 2 terms in here, it will be the Hayami equation, kind of roughly. Actually, no, because the Hayami equation has the convection of the surface water. Here, it's something else in here because this is groundwater. This is not a surface water problem. But in 2 dimensions, equation 1 simplifies to this equation. We get rid of the z over there. Same thing. There's no variation on the z, therefore the c, it's dropped out of the question. Now, if we assume a homogeneous isotropic aquifer of hydraulic conductivity K, then we further simplify this. We pull the Kx and Ky and call it K, and we pull it outside. And now we get a true second order, so-called diffusion equation. Okay, defining the hydraulic diffusivity of the aquifer freeze and cherry as follows. Okay, this is a situation. People talked about the K and the S sub S. The K is the hydraulic conductivity, L over T, feet per second, the speed through the porous media. And S sub S is the specific storage. But they did not associate them together. Only Freeze and Cherry, when they came out with a book in 1979, they defined the hydraulic diffusivity because, in fact, K over S sub S is a diffusivity. K over S sub S is a diffusivity. It has the units of L squared over T, which leads to this. So we were going to simplify the equation and call it a diffusivity. We'll quote it Freeze and Cherry. Freeze and Cherry are 2 professors in the US that in 1979 came up with the definitive, at the time, book on groundwater. They call it Groundwater. I read the book entirely. I thought it was a great book. They're good authors, Freeze and Cherry. I don't know, 79, they're probably already, God knows what happens. But the point is that that was a good book, and we used the concept of nu, which is the hydraulic diffusivity of the aquifer. So equation 5 represents 2-dimensional flow in a homogeneous isotropic aquifer of properties K and nu, and source sink term W. You can see K, nu, the sink term, the diffusivity, the second order, everything is structured nicely for this equation 5. Now, here's the crux of this whole thing. A simple and appropriate finite difference scheme of first order in time and second order in space. Remember that if you want to center a scheme, you got to do it at second order in time and second order in space. But if you did that, you'll end up with a Richardson scheme, which is unstable, eventually unstable. At the beginning it works and then it drops all of a sudden, like accidentally, right? So we don't want to get into Richardson's again. We remember, we already talked about that. So we need to provide some offsetting. The offsetting gives us stability. You can use a weighting factor, and people have used weighting factors beginning of the work of Priceman in 1961. But other people you do it this way. They say, let's do a first order in time and second order in space. And that would be offset already. The centroid of gravity of the scheme would not be on the floor. It would be high up a little bit, like this. I'm looking at it right now. We have in here jkn over here. Jk plus 1n, jk minus 1n, j plus 1kn, j minus 1kn, right? Those are the four values that are going to be taken. And then above, on the advanced level, we have jkn plus 1. If you look at these indices or sub-indices in here, you'll see that it makes sense. Again, I repeat, in the center, jkn. Advance one time, jkn plus 1. Then forward over here on the x is j plus 1, j minus 1, and on the y is k plus 1 and k minus 1. So now we're going to come up with this term in here is these terms in here. Now, and I have changed this. I put this, the right-hand side, put it on the left. I don't know why I did that. It's kind of confusing. Well, most people, no, I should take this back. I should take this and reverse it. Delta H over delta T equal to this so that it could translate directly into the next equation. I'm going to do that because it doesn't really matter how you express equation 5. Okay, so we get equation from equation 5 numerically, digitally, with digits, we get equation 6. Why? Because we have the h dt, which is n plus 1 minus n, right? That's dt over dt, derivative with respect to time. And then the second order derivatives is this. It's the change of the change. Now, you want to do this, you could. If you're not familiar with this, you could actually sit down and do it. You take the first derivatives, and then you take again the derivatives of the first derivatives, so you can get the second derivative, and therefore you get this like this. It's like hj plus 1k minus hjk minus hjk minus hj plus 1, but the minus changes to plus, and the other one changes to 2. So anyway, everybody in numerical analysis is very familiar. This formula here is very familiar. I learned it very early in the game. So this is a formula that replaces this formula over here. This is the partial differential, and this is the digits, the digit of the numerical scheme. So that works. That works. The spatial interval, we're going to stop in here pretty soon. The spatial interval is set equal, delta S equal delta X equal delta Y. Now, following Roach, who in 1972 wrote a very good book called Computational Fluid Dynamics. I don't know if he ever reissued it. He didn't publish it. That's fascinating. I should reveal to you at this time. I don't really know this stuff. Maybe I shouldn't say anything. But his book was not published by one of the great publishers like Prentice Hall or McGraw-Hill. And I don't know why. But he did publish a book by some second-rate publisher or less popular publisher. I have the book somewhere. I read it extensively at the time, back in the 70s, middle 70s. And he has this concept in here. The ratio of physical and numerical diffusivities. We defined a type of Reynolds number. Now, he defined the Reynolds number in the opposite way. He defined it with a numerical to physical. But that's why we call it, we define a type of Reynolds number. And we call it a Reynolds number because he called it a Reynolds number. So basically, we did not come up with the concept, we did not originate the concept of Reynolds number. We borrowed it and changed it a little bit from Roach, which is a very well-established book. This leads to physical diffusivity over numerical diffusivity. Now the question is how to define the numerical diffusivity. When we were using the Courant number, we say delta X over delta T, fine. But in here, gets a little bit more complex. And we're given to understand that what we have to put in here is the half of the delta X or half of the delta S. It has to be half in there. For kind of the same reasons that the diffusivity of Hayami is Q sub naught over 2 S sub O. What does the 2 have to do in there? At one time, I decided that I was going to get rid of it. And I finally end up getting nowhere. The 2 belongs there in the Hayami formula. Likewise, the 2 belongs here in this formula. So if you run the math in here, you end up with this definition of the number. 4 nu times this. And then equation 6 reduces to this with the algebra, right? Reduces to that, in which the h bar over here, do you see the bar in there? It doesn't quite show itself. In which the h bar is just the average. Just the average. In other words, the average of these 4 values, 1, 2, 3, 4. That's the average. So the final formula is the d, our cell Reynolds number, times the average, plus 1 minus d times the central value, plus the source term. And that's equation 8. Okay. And then we have to work on the source terms need to be handled carefully, by the way, because they have to follow the units. If you don't follow the units, you're dead in the water. Nothing has ever happened. So I'm not going to have time in here to follow the units. I urge you to look at this and see if you can indeed follow the units. But the units, the equation has to be a homogeneous equation and physically homogeneous. In other words, an absolute requirement is that the units be dimensionless or they fit. Other than that, they also have to be physically based, but they have to be dimensionless. I guess, I don't know if it makes sense or not. But okay, so the time average sink, likewise in here, let me give it one more minute in here. Transmissivity and diffusivity, and equation 8 reduces to the following. So this is amplifying the equations in order to take care of the source and sink terms. So for the special case, and we get this in here. Okay, so that's it. That's where I'm going to leave it. And when I come back, I've got about 40% on this paper. So the rest we'll do on Thursday. And then after that, we will move on to the next section because we're going to have time. We're a little bit ahead of our time here.